Yeah, good morning, everybody. So I want to thank Dr. Saleh for allowing me to give today's lecture. We all know that OCT was first demonstrated for cross-sectional imaging of the retina in 1991 by MIT. And ever since then, when there was an FDA clearance in 2002, it has become a very clinically useful diagnostics tool in ophthalmology community. And it has undergone over the years a very substantial advancement or improvement in the last decade. And it has now become a very important adoption in the various other clinical and research applications. So we have seen over the time there has been extensive development of the next generation technology in OCT. The key has been the high-speed imaging. The high-speed imaging has brought about a lot of change in approach towards the OCT technology. And this has been able to, as my earlier speaker has also shown, that is able to generate three-dimensional volumetric images. And these volumetric images and averages to give a wonderful depth penetrating OCT. What has been achieved is with the Fourier domain technology, which has given rise to what we know as the spectral domain OCT or the SDOCT or the swap source OCT. And this has been shown that after the advent of this OCT, there's an extensive publication which has come, which implies that the technology has brought about an immense effect in our clinical practice. So we also know the retinal OCT imaging provides a very high resolution imaging of the interretinal structures, and which is not accessible with fluorescent angiography. As you can see over here, the shows allows the differentiations of every layer of the retina. And so the current trend has demonstrated over the years there's an increasing tendency to incorporate this imaging into our clinical studies. And primarily, it is able to capture treatment change in the retina after treatment, especially in the micrometer scale. So what is a technological advancement which has occurred over time in the retinal imaging with the OCT? We all know at the high-speed 3D OCT, which is a spectral domain OCT, which we're using. What is important is the upcoming of swap source OCT, and adaptive optical OCT is a very interesting tool in cellular imaging, as well as polarization sensitive OCT and OCT angiography. I would like to highlight a few of these just to give an insight. We know that swap source OCT is a form of Fourier domain OCT, but it employs what is important is a very fast scan pattern. It goes up to almost 400,000 scans, exascales per second. So primarily because it uses a tunable laser up to 1050 nanometers, so the depth penetration is very high. Because of a faster scanning speed, it eliminates the signal drop. So many times with spectral domain OCT, you might have some distortion because of the signal drop penetration. And we know because of a shorter scanning time, you are able to reduce the image distortion, allows to improve the scan quality for visualization of fine structures. So swap source OCT uses, in many of the swap sources, it uses a light source at the level of 1050 nanometer. And the spectral domain OCT primarily uses a spectrum up to 840 nanometer. However, spectral domain OCT, if you use the EDI, you can have the same penetration as a swap source. So this has been shown recently that spectral domain OCT is not as good as a depth penetration identifying the sclera and the choriocapillaries as with the swap source OCT. And if you use an EDI OCT with the spectral domain OCT, you can have a similar depth penetration of the choroidal thickness measurement in comparison to the swap source OCT. What it implies the swap source OCT is pretty good in imaging the outer retina and the choroidal layer. What is more interesting is adaptations of this adaptive optics OCT. Adaptive OCT has a transverse resolution. The OCT is limited by the spot size. Because of the small spot size, you can do a cellular imaging. Here the laser beam is, we know when you use it, you might have optical aberrations when it passes to different media. And there is a problem in the transverse resolution. So adaptive optics uses an optical to correct these optical aberrations and improves the transverse resolution. That is what is the advantage over other mode of imaging. and as a result of which we get a very high quality image, and it can help us to visualize the retinal microvasculature, photoreceptors, laminar cribbos, and other ganglion sense layers microstructures. So we can have a three-dimensional cellular imaging of the retina. You might be able to understand now how important and interesting it is for those people who are working on research in the photoreceptor level. So what it shows that it uses a wavefront sensor, as you can see over here, wavefront sensors to avoid the aberration which you get, and you get a high lateral resolutions. As we all know from before, when we got Stratus OCT users, we use a coherence interferometer using a two reflectance mirror with the optical waves, so the depth penetration resolution is pretty less. This is what it shows when you have a cross-sectional images using an adaptive optics cross. You can see the blood vessel over here, which is well seen on the cross-section. It's a spectral domain OCT. But what is important is that when you do a cross-section on a single area, you are able to do a transverse or the end face, and you'll be able to see below the RP each layer, and even the ganglion cell layer. So it is so important in clinical research too right now to go and with the invention of this adaptive optics. What is more important is that you are able to do the imaging of the photoreceptors. So the cone receptor disease or the outer segment disease can be easily be understood, and this has become very important in genetically linked disease to the photoreceptor. So it is still a maturing technology and increases the imaging, which is capability of 3D cellular imaging. Now, what is polarization OCT? Polarization OCT, sensitive OCT has already been installed in some of the machines. You can change. What is allows the differentiations of the different tissues and generates images with tissue-specific contrast. So it has distinguished the ocular structure based on the property of the polarization. What you will see over here, that when you see the sclera and the retinal nerve fiber layer, as you can see over here, you will have a birefringence property, and the photoreceptors will have polarization preserved, which you don't see, and then the RP shows RP polarization. And that is what you see in this example in the dry age-related macular degenerations, where you hear bandwidth beyond the polarizations in the area over here, which is a limited RP atrophy. Over the wider RP area, the bandwidth, which is larger, it is seen, and on the end face of the transverse scan, you can see the area which you can map. What is more interesting over time now is the OCT angiography without using any dye. So it's a high resolution, non-invasive angiogram, qualitatively similar to fluorescent angiography. It can visualize microstructure in the retina and your choriocapillaries. It uses a motion contrast from the fluctuation on the intensity of the versus time on the flow of the blood. So it's a very powerful tool to visualize and investigate the outer retinal layers and the choriocapillaries, primarily because it uses an ultra high speed swept source OCT or a spectral domain. What is the advantage of this? Advantage is it doesn't require an exogenous contrast. It can, imaging measurements can be safely and repeatedly be done, and can image a three-dimensional vascular structure. So we can see the choriocapillaries and the abnormality, and can even follow if there is a slowness in erythrocyte flow, which you can pick up at the early, if there is any early block in the vasculature. So basically, it may be possible that this technology may help you to detect local perfusion defect early. The disadvantage is that it does not dye doesn't leak. So fenestrated choriocapillaries, you will not be able to know whether it's leaking more than usual. So what is seen? And this has been shown in the recent publications. As you can see over here, very interesting, on the fluorescent angiograph, you see two focal leaks, which are kind of a type 3 neovascularization, or what we know as retinal angiomatous proliferations. But when you do the OCT, the spectral, you will see the interretinal neovascularization now over here, and the other one small, which is over on this spectral domain. But when you do an end phase or the transverse scan, swab source, OCT, and geography, what you see over here, you can see the high flow lesions. You can see have very nicely been seen at the level of choriocapillaries. We know that the type 3 neovascularizations grows from the choriocapillaries under the RPE. When it coincides with the RPE, sub-RPE, CNV, then it becomes a type 2 CNV. So, and you can see over here, even the post-treatment, you can see the choriocapillaries and geography. You can see the lesion over here after treatment decreases. So what it means that it is also an important tool, is still growing and is capable of demonstrating flow in the early type 3 neovascularizations, so we can quantify the reduction in the flow pattern. So what does this swab source or the OCT and geography do? What it does, it takes a multiple B scan at a single point, and it does an averaging and does a volumetric analysis. When it does a volumetric analysis on the transverse of the end phase scan, when you go below the RPE, you'll be able to see these choriocapillaries. But while you're doing that, you can get a speckle decorrelation. Speckle decorrelation is because of the blood vessels which you see on the retinal surface, which is seen over this. This is not the part of the choriocapillaries. So when you do montage, you will see. So what does it show us? It shows us that it gives you immense way to understand diseases at the level of the outer retina and the choriocapillaries. But the problem is that it is only in the focal area. So many things needs to be done. When the speed, high speed is increased, probably you can increase the size of the scan. So what we understood from this, we understood that it's still evolving with the very innovative applications in our day-to-day OCT, and further advancements in OCT technology and imaging speed are expected. Probably we increase the larger retinal scanning, and it has a very important role right now in detection, quantification of retinal disease during the course of treatment. Presently, OCT is an integral part in the management of retinal pathology. I thank you for your patient hearing.